Hi everyone, this is the practice test for test 2. First question is asking for the Lagrange function that is needed to find the maximum of a given function, of the objective function, subject to the constraint. Our Lagrange function, capital F, is written as our objective function, the function we're trying to find the max or min of, so in this case little f, plus lambda multiplied by our constraint, g. In order to pose the constraint in a way that is compatible with this equation, we have to take our constraint and write it as being equal to 0. So we need g equal to 0. So we're going to have x, y, z minus x minus y minus 1 equals 0. Subtract 1 from both sides. So that's our g. That's our g function. Now we can plug everything in. Our function is x to the y plus y squared plus z squared, then plus lambda times our constraint. X, y, z minus x minus y minus 1. So that would be choice E. Next question. Number 2 says, find all the critical points of the Lagrange function whose partial derivatives are given by, and it gives the x derivative, y derivative, and lambda derivative of the unstated optimization problem. All that we have are the first derivatives. The easiest way to solve one like this is to take the first two, the fx and the fy derivative, set them both to 0, and simultaneously solve them. So x squared plus lambda y is 0, and y squared minus 8 lambda x is 0. In the first equation, I'm going to isolate it for lambda. So lambda y is equal to negative x squared. That means lambda is equal to negative x squared over y. Do the same thing with the second equation and isolate it for lambda. So we have 8 lambda x equals y squared. Then divide both sides. So lambda is equal to y squared divided by 8x. Now the lambda has to be the same in both of them. So I'm going to set lambda equal to lambda. That means negative x squared over y is the same thing as y squared over 8x. Now we'll cross multiply. We have negative 8x to the 3 equals y to the 3. Then you can take the cube root of both sides. Cube root of negative 8 is negative 2. Cube root of x to the 3 is x. Cube root of y to the 3 is y. That gives us a relationship between x and y, and we can use that relationship inside the f sub lambda equation. F sub lambda, which we also have to set equal to 0, it is xy plus 72. So we have 0 equals x times, and we'll replace y with negative 2x plus 72. Add the negative 2x squared to both sides, so positive 2x squared is equal to 72. Divide both sides by 2, x squared is equal to 36. And that's going to be true when x is 6 or negative 6. Now for each of those x values, we get an associated y value. Up here it says y is equal to negative 2x. So if x is 6, y is going to be negative 2 times 6, which is negative 12. That gives us one of the points, 6 comma negative 12. And if x is negative 6, then y is going to be negative 2 times negative 6, which is positive 12. So our second point is negative 6 comma positive 12. So we're looking for 6 negative 12, negative 6 positive 12, which is choice D. Okay, next one. Number 3 we're given the function x squared plus y squared minus 4xy, and we're asked to optimize it subject to a constraint, where the constraint is given by x squared plus y squared minus 12. The critical points are given, so they tell us that negative root 6, and the other three, these three points are critical points of the Lagrange function. Then it asks, based on the information, which of the following is true. Which one's the max, which one's the min. Now, this step of the problem is the very final step. You take the derivative, set them to 0. You do all that stuff. You get your critical points. Then, in the constraint optimization problems, you sub the critical points back into the function that you're looking for the max or min of. So in this case, little f. And you simplify. So I'm going to plug each of those 4 points in. We're going to plug f of negative root 6, comma, positive root 6 into the original function. So that's going to be root 6, negative root 6 all squared, plus positive root 6 all squared, minus 4 times negative root 6 times positive root 6. Check, okay. Then simplify. That's going to be 6 plus 6, and then we have plus, negative times negative cancels, root 6 times root 6 is 6, 6 times 4, 24. So we end up with 36. So keep going. Plug in the next point, f of root 6, comma, negative root 6. So we'll get the same thing in different order. So we get positive root 6 squared plus negative root 6 squared minus 4 times positive root 6 times negative root 6. And then we simplify that. We get 6 plus 6. And then again plus. Two negatives cancel. Positive x is root 6 times root 6. 6 times 4, 24. We again get 36. Now we try the other 2 points. So our function evaluated at negative root 6, comma, negative root 6. So that's going to be negative root 6 squared plus negative root 6 squared, and then minus 4 times negative root 6 times negative root 6. That will be 6 plus 6, and then the 3 negatives multiplied together will give you a negative 24. So that's 12 minus 24, which is negative 12. And we got one more to do. We have to plug in the last critical point, root 6, comma, root 6. And when we do that, we're going to get positive root 6 squared, 6, and then another positive root 6 squared, 6, and then minus 4 times root 6 times root 6. So 12 minus 24 again, which is negative 12. And we compare them. Circle the 4 of them. We have a z value, a height of this function at this point of 36 and 36 at the first 2 critical points, and a height of negative 12 and negative 12 at the second 2 critical points. So negative 12 is the global min, the minimum of the function, and 36 is the max. The max occurs twice at 2 different values. The min occurs twice at 2 different values. Option 1 says the max is 12, but it's not. The max is 36. Option 2 says the max is negative 36, but it's not. It's positive 36. C says the minimum is 36. It's not true. It's 36 is the max. And then D says the minimum is negative 12, and that one's true. So the key for these types is to plug the critical points into the little f function, the function that we're looking for the max of, or the min of, and then ranking the output whatever number is coming out of that function evaluation. Okay, second question is, fourth question is finding the exact value of two trig functions divided by each other, evaluated at particular angles. First one is cosecant. So I'm going to calculate each one of these separately. Cosecant of 7 pi over 6. 7 pi over 6 is a reduced fraction, so we can use a trick. It's going to be, well, before we use that trick, I'm going to rewrite it as 1 over the sine of 7 pi over 6, and now we'll use the trick. That's going to be 1 over plus or minus the sine of pi over 6. Now, we have to decide if there's a positive or negative sign in front here. That requires thinking about angle diagrams. And where on the cast circle is 7 pi over 6. So let's go to 0, start there, and pi over 6 is 30 degrees. Here's the first increment of 30. Here's the second increment of 30 to 60. Third one up there. Now we're at 90. 120, the fourth one, 160, 5. The sixth one, we're at 180. And for the seventh one, we are inside the T quadrant. This angle was 7 pi over 6. In the T quadrant, sine of the angle is negative. Only the tan function is positive. So we get a negative sign in front of the pi over 6. Okay, we'll keep going. Sine of pi over 6 comes from your 30, 60, 90 triangle. And you get 1/2 from that. So 1 over negative 1/2, which is negative 2. So we get negative 2 on the top. Now we have to do secant of 5 pi over 3. We'll do that as a separate calculation. Secant of 5 pi over 3. That's 1 over the cos of 5 pi over 3. Which is, we're using a trick because 5 pi over 3 is a reduced fraction. We can write this as plus or minus 1 over plus or minus the cos of pi over 3. So we need to decide if we're going to put a plus sign or a minus sign in front. So again, we draw out our cast circle and count up the angles. So this is for 5 pi over 3. Pi over 3 is 60 degrees. Here's the first increment of 60 degrees. Now the second one brings us to 120. Third one brings us to 180. Fourth one puts us inside the T quadrant. And then the fifth one puts us inside the C quadrant. Inside the C quadrant, cos of that angle is positive. We put a plus sign in front. Now, pi over 3 is also in the 30, 60, 90 triangle. And when we draw it out, we'll find cos of pi over 3 is, well, 2. And then 1 divided by 1 over 2 is 1 multiplied by 2 over 1, which is positive 2. We'll skip that step for the previous one. Anyway, we can combine these results now. So going back up to the top left. So we're in this region, top left. Cosecant 7 pi over 6, we found that that was negative 2. And then secant 5 pi over 3, found it was positive 2. So that gives us a negative 1. So E is our answer. Okay, number 5. We're asked to take the derivative of sine of 2x. So I'm going to write this as f of x is the sine of a function w. When we take the derivative of sine is cosine, but because it's a cosine of a function w, we have to multiply by w prime using the chain rule. Then we can plug in what we have. Cos of 2 to the x multiplied by the derivative of 2 to the x. And the derivative of 2 to the x is 2 to the x times the ln of 2. And we look for an option that looks similar, maybe in a different order of multiplication. So 2 to the x times the ln of 2 times the cos of 2 to the x. 2 to the x times the ln of 2 times the cos of x, or option D. Okay, next one. Number 6. We're asked again for a derivative of a trig function. This time it's the log of a trig function. F of x is the ln of w. When we take the derivative of the ln of w, it's w prime over w. And this is going to get ugly. The bottom, w is just the function that's inside. So cosecant of x plus cotan of x. Now upstairs goes the derivative of what's inside. Derivative of cosecant of x is negative cosecant of x times the cotan of x, and the derivative of cotan is negative cosecant squared of x, which is almost option B. So option B is wrong. It has a plus sign and it should have a minus sign. That means we have more work to do. I got some emails about this. Well, how come there's a typo in B and there's not? You have the common factor. So on the top, on the numerator, and the common factor out cosecant of x, or actually negative cosecant of x, we factor it out. In the first piece, in the numerator, we're left with a cotan of x. In the second piece, we're left with plus cosecant of x. We factor the minus sign out. And downstairs, nothing changed. I'm going to put brackets around it though. Cosecant of x plus the cotan of x. And the order of addition doesn't matter. A plus b is the same as b plus a. So that cancels. Now we're left with one of the options, negative cosecant of x. Okay, next one. Number 7. We're asked to solve the differential equation. The derivative of a mystery function is 16x to the power of 7 minus 6x, or a given piece of information, f of 1 is equal to 11. Here we go. We're going to start by taking the antiderivative of the derivative. We're going to take the antiderivative of 16x to the 7. Derivative of x to the 7 is 1 over 8 x to the 8. Derivative of x is 1/2 x squared. And we need a plus c. Let's clean that up. 16 over 8, 2, x to the 8. 6 over 2, 3, x to the 2 plus c. Now we're going to use this information that f of 1 is equal to 11. That means we set our function equal to 11 and our x value is equal to 1. And then we're going to rearrange this and solve for c. So we have 11 equals 1 to the 8, which is 1 times 2, so 2, minus 3 plus c. So 11 is equal to negative 1 plus c. That means c is equal to 12. So our function is f of x equals 2x to the 8 minus 3x squared plus 12. That function satisfies both the derivative condition and the condition on the function at 1. Option A. Okay, number 8. Often with integrals, it's not going to be clear if you should do a substitution or if you try to simplify first. For this one, it's one term on top minus another term on top divided by the one term on the bottom, it can be simplified. So you can rewrite it, and there's different ways of doing this. You can rewrite it as integral of 6x over 3x squared minus 12 over 3x squared. If you have two pieces in the bottom, you can't do this. You can't split up two parts downstairs, but you can split up two parts upstairs. Now we simplify. Antiderivative, 6 over 3, so we have a 2 upstairs, and an x downstairs, x to the power of 1 in the basement. And then 12 over 3, 4 over x to the power of 2, and rewrite that as 4x to the negative 2. Yes, we can write the first one as x to the power of negative 1, but I'm not going to do that. Now we take the antiderivative. Antiderivative of 2 over x is 2 times log and absolute value of x. The next one, antiderivative of x to the negative 2, we increase the power by 1, so negative 2 plus 1, negative 1, and then do 1 over that new power. And then plus c. We can clean that up. That middle term is a bit of a mess. 2 times log absolute value of x, minuses cancel, plus 4x to the power of negative 1 plus c, which is 2 times log absolute value of x plus 4 over x plus c. Choice B. And looking at the options, the part that's treated as the tricky part is taking the antiderivative of 4x to negative 2. Okay, the next example, number 9, is also the type of problem that you have to simplify the integral first. One piece is not directly the derivative of another piece. You can't set it up as a reverse chain rule. That's what a substitution does. So we're going to FOIL the inside of that integral, in the integrand. E to the x over 2 minus 5 multiplied by e to the x over 2 plus 5. So first times first, e to the x over 2 times e to the x over 2, and then outside two terms plus 5 e to the x over 2, and then the inside two terms minus 5 e to the x over 2, and then the last two terms minus 5 times positive 5, negative 25. So the middle two terms destroy each other, and we have e to the something times e to the something else. The exponents are going to add. The x over 2 plus x over 2 minus 25, which is e to the x minus 25. Half of x plus another half of x is a whole x. Now we can rewrite our integral as integral of e to the x minus 25 dx, which is e to the x minus 25x plus c. Antiderivative of 25 is 25x, antiderivative of e to the x is e to the x. So choice D. Okay, number 10. Antiderivative of secant squared minus antiderivative of cosecant squared. So, d by dx of what equals secant squared? The answer for the what part is tan of x. The derivative of tan of x is secant squared. So this integral is going to be tan of x for the first part. Antiderivative of secant squared is tan. Now we need the other part. D by dx of what equals negative cosecant squared of x. And the answer there is cotan. So plus cotan of x plus c. If the question originally had a plus sign in between, we'd have to have a minus cotan of x. So choice C. Something that's helpful to help, I guess, memorize these trig derivatives is if you take the derivative of a trig function that contains the letter t, tan and cotan are the only ones that do, then the resulting function will be something squared, secant squared or cosecant squared. If your function starts with the letter c, when you take the derivative of that function, there'll be a minus sign in front. When you take the derivative of cos, you get negative sign. When you take the derivative of cotan, you get negative cosecant squared. When you take the derivative of cosecant, you get negative cosecant times cotan. So there's no cosmic reason for that. It's just a fluke. There's no greater meaning to it. Number 11. Antiderivative of e to a power of a function divided by something that might be related to the derivative of that function. And you look at the options, all the options are inviting a substitution of some type. There's several ways to solve this one. I'm going to show you one way. I'm going to let w, and I know in some classes you use w, in some classes you use u for your substitution, in some classes you use t for the substitution. It doesn't matter what letters you use. I like to use w for it. I let w equal the power inside the exponential function, 8 times the square root of x plus 1. And I'm going to write it as, instead of a square root of the power 1/2. So when we do that, we can start our substitution off. We have e to the w over the square root of x plus 1. Now we have a problem. We have a dx that is not in terms of the variable w. Here's another variation between the way that some people do substitution. Sometimes in some classes you don't substitute dx the way that I'm about to show you. You substitute dx divided by the square root of x plus 1. You substitute that as something. I'm just going to do it the way that I like to do it. So I want to wholesale replace dx with something else, with dw times stuff. My first step in doing that is to take the derivative of w, using the notation that you might not like still. Instead of w prime, I'm writing it as dw by dx. When I take the derivative of function to a power, the power comes down. So the 1/2 multiplies by the 8, we get a 4. And then we have original function, x plus 1, to the negative 1/2, power gets reduced by 1, and then we multiply by the derivative of the inside. The derivative of the inside is 1 plus 0, so 1. Okay, I'm going to rewrite that. dw by dx is 4 divided by the square root of x plus 1. Power negative 1/2 means the square root downstairs. Now I'm going to rearrange this to get dx all by itself. Cross multiply. Square root of x plus 1 times dw is equal to 4 times dx. Then divide both sides by 4. So dx is equal to the square root of x plus 1 times dw all over 4. And there's my object that I'm going to use to replace the dx. dx gets replaced by the square root of x plus 1 times dw all over 4. A good substitution is one that when you want to rewrite your function in terms of a new variable, in this case w, the substitution eliminates all of the old variable, in this case x. So no x stuff is left. The square root of x plus 1 upstairs cancels with the square root of x plus 1 downstairs. Now there's a 1 over 4, and there's a 4 downstairs. I'm going to put that in front to make the integral clean. So 1 over 4 in front of the integral, and what's left inside is just e to the w, dw. Okay, that's the hard part. Now we take the antiderivative of e to the w, and the derivative of e to the w is just e to the w, and then we have a plus c, and we can reverse our substitution, and we can put w back as what it was. E to the 8 times the square root of x plus 1 plus c. So the 1 with the 1 over 4, option B. Okay, number 12. also invites a substitution. Here you see that there's a 5x plugged into secant and plugged into tan. I'm going to let w equal 5x because it's plugged into a function. Then dw by dx is 5. So dw is equal to 5 dx, and dx is equal to dw over 5. There's cross multiplying and cross dividing to isolate for dx, because ultimately when you do a substitution using this approach, you're going to have to replace dx with something else. So I have 25 secant of w times the tan of w times my replacement for dx, dw over 5. Okay, there's no x stuff to cancel out. All the x stuff was done with when we substituted in w for 5x. No x stuff lingering around. We can clean this up a little bit. 25 over 5 is 5. I'm going to put that 5 out front of the integral. We have secant of w, tan of w, dw. So successful substitution, we've simplified the function. Now the question is, the derivative of what is secant of w times the tan of w? And the answer is secant of w. Something to memorize. Derivative of sec of w is sec w tan w. We get a plus c, and then we can reverse our substitution. 5 times the secant of 5x plus c. And that would be choice C. Okay, number 13. This one's an antiderivative with bound for integration, also called a definite integral. The way to solve these is to take the antiderivative and plug in the bounds. Integration, plug in the top number, plug in the bottom number, and subtract. So I'm going to take the antiderivative piece by piece. From the first piece, antiderivative of x to the 3 is 1 over 4 x to the 4. And that's multiplied by the 4 in front. Antiderivative of x is 1/2 x squared, multiplied by the 20 that's in front. Antiderivative of 1 is just x. And then we evaluate, so the vertical line is a symbol that means evaluate from -1 to 3. Okay, before plugging those numbers in, I'm going to clean up what's inside. 4 over 4 cancels, we get x to the power 4. 20 over 2 simplifies into 10. And x is pretty happy already. So -1 to 3. Now plug in the bounds. Oh, where'd the x squared go? I lost an x squared. I gotta go fix it. 10x squared. There. Okay, now plug in the bounds. We're going to get, from the top bound, we have 3 to the power of 4, which is 81. 3 times 3, 9, times 3 again, 27, times 3 again, 81. Now plug 3 into the next piece. -10 times 3 squared, that's -10 times 9, that's 90. And then plus 3. Then plug in the lower bound and subtract what comes out. -1 to the 4 is +1. -1 to the 2 is +1 times -10, so -10. And the last piece, -1. Okay, now simplify. We have, let's see, 81 minus 90 plus 3, so -6. The first bracket. Now we have minus -10. So that's going to be -6 plus 10, which is +4. Choice A. And number 14. 14 is the type that resembles 1 over x, resembles a log function. You take the antiderivative of 1 over x, you get ln of x, but there's stuff kind of contaminating it. And the bounds are ugly. I'm going to do this as a wholesale substitution. Everything is going to be substituted in. We're going to change the bounds. So this integral, my starting point is, I'm going to set w equal to everything in the bottom. W equals 2x plus 1. Then dw by dx is equal to 2. Rearrange, and you get dx is equal to dw over 2. Cross multiply and cross divide. So that's going to be my replacement for dx. Now for the bounds. We're going from the x variable to the w variable. The top bound says x is equal to e over 2 minus 1 over 2. And w is equal to 2x plus 1. We're going to have 2 times the x, e over 2 minus 2, or minus 1 over 2, and then plus 1. The 2's cancel. We're going to have e minus 1 plus 1, which is e. So our top bound is e. Might as well start writing this integral out. This equals integral. The top bound is e. The function is 10 over w. And our dw, or our dx gets replaced by dw over 2. Red. Now we need the bottom bound. The bottom bound is a bit different. It's 1. So w is equal to 2 times 1 plus 1. W is equal to 3. So integrating from 3 to e. Now, let's clean this up a little bit. Lots of numbers floating around. 10 over 2 is a 5 in front. 5 upstairs. Integral from 3 to e of 1 over w dw. Antiderivative of 1 over w is ln absolute value of w. We do not need a plus c whenever there's bounds of integration. We just need to evaluate this on the bounds from 3 to e. Now we plug in the top bound and plug in the bottom bound and subtract. 5 times ln of e. I can drop the absolute values because e is a positive number. Minus 5 times ln of 3. I can drop the absolute value 0 because 3 is a positive number. And then simplify. Ln of e is 1. 5 times 1 minus 5 times ln 3. So we get 5 minus 5 ln 3. Choice D. Now when you do this type of substitution and you change the bounds of integration to be represented in terms of the new variable, you do not take your antiderivative, your ln w, and convert it back into ln of 2x plus 1. You don't convert it back to the x variable unless you also want to convert your bounds back to the original bounds. And you did all that work basically for nothing. Number 15. There's two normal ways to do this. Normal way number 1 is to expand out the second term. X to the 5 plus 10x times itself 5 times. And then multiply that by x to the 4 plus 2. And then take the antiderivative term by term, and then try to refactor it all. So that's one of the quote-unquote normal ways to do it. Here's a better normal way to do it, a substitution. Notice that the function that's inside the brackets, the power 5, is related by its derivative to the function that's beside it, x to the 4 plus 2. Take the derivative of x to the 5 plus 10x, you're going to get 5 multiplied by what's inside that first bracket. So there's a relation between these two pieces. That means a substitution is likely to work. Now let w equal the thing inside the second bracket, the thing that's inside the power of 5. The x to the 5 plus 10x. Because that thing is raised to a power, that's a function plugged into another function. I'm going to calculate the derivative. dw by dx. Derivative of x to the 5 is 5x to the 4. Derivative of 10x is 10. Now we cross multiply. Cross divide. Well, I'll common factor first. I'm take a 5 out. 5 times x to the 4 plus 2. Now let's rewrite what's going on here. We have dw by dx is equal to 5 times x to the 4 plus 2. I want to get dx all by itself. I want this piece to be isolated. So dw is equal to 5 times x to the 4 plus 2 times dx, and then divide both sides by the thing that's multiplied by dx. So dx is equal to dw over 5 times x to the 4 plus 2. And that will be my substitution. I'll take all that stuff and replace dx with it. So this converts into an integral of the first piece we did not touch. X to the 4 plus 2 was not part of our substitution. The second piece we did touch, we called all the stuff in the second bracket w. So this is w to the power 5. And then we need a dx to be replaced by what was just found off to the right. dw over 5 times x to the 4 plus 2. And that's why I common factored it. Common factored it earlier so that the cancellation would show up easily at this stage. There's a 5 downstairs, so I'm going to put 1 over 5 in front of the integral. 1 over 5 integral of w to the 5 dw. Antiderivative of w to the 5 is 1 over 6 w to the 6. And we get a plus c. And then that's going to be 1 times 1, 1. 5 times 6, 30. W to the 6 plus c. Got one more step. And that's to replace w with our original substitution, which was x to the 5 plus 10x. So our answer is 1 over 30 x to the 5 plus 10x all to the 6 plus c. And hopefully we have one of those. Option E. Okay, 16. 16 is kind of a trick question. It wants, or it doesn't want, it says the antiderivative of a mystery function is e to the 2x plus c. Find the antiderivative of the same mystery function evaluated on the bounds. Well, what we would normally do is we would take the antiderivative and plug in the bounds, but the antiderivative is given to us. It tells us the antiderivative is e to the 2x plus c. Whenever you have bounds of integration, you don't need the plus c, you can drop the plus c. So all we have to do is plug in the bounds of integration. The antiderivative part's done for us. It was done in the question itself. They told us what the antiderivative was in the first part. This is not saying the antiderivative of e to the 2x evaluated from ln 2 to ln 5. This f of x that's in there is not e to the 2x. It's a mystery function. We could find it fairly easily, but we don't need to. Anyway, now plug in the bounds. So e to the 2 and x gets replaced by ln 5 minus e to the 2 and x gets replaced by ln 2. We had some stuff like this on the first test, where we had to simplify expressions like this. The way we simplified them was we brought the power, the number, in front of the log function up as a power. So we have e to the ln of 5 squared minus e to the ln of 2 squared. Now we use the cancellation law. E ln cancels, E ln cancels. And we get 5 squared, 25, minus 2 squared, 4, which is 21. Option E. Okay, and then 17. New type of problem this week. You would have seen this in Monday's class or Tuesday's class, depending on your section. It's an absolute value integral. And the way to handle absolute value integrals is to split the integral up into two absolute value of x is a piecewise function. It's equal to positive x. You give it a positive x value. So absolute value of 5 is 5. And if you give it a negative x value, to make it positive, you just multiply it by negative 1. So you can replace x with negative of x, if x is already negative. So absolute value of negative 7, that would be negative 7, so positive 7. We can rewrite our integral as an integral that's split from minus 5 to 0, where the piecewise function switches at 0, of f of x dx, plus the integral from 0 to 5 of f of x dx. I'm running out of space. I'll carry this over here. Now, what is f of x in the first part? Integral from minus 5 to 0. So we're looking for what the function is doing between negative 5 and 0. Between negative 5 and 0, that's x values that are less than 0. So our function, our absolute value of x function, gets replaced by a negative x. And then the second part, from 0 to 5, that's for values of x that are positive. So our function gets replaced by a positive x. Okay. Just check the time here. Okay. I put the negative sign up front. It's not a bad idea to factor constants in front of integrals. So we have integral from negative 5 to 0 of x dx plus integral from 0 to 5 of x dx. Now I'll take the antiderivative of each piece. Antiderivative of x is 1/2 x squared. I'm going to go from negative 5 to 0 plus another 1/2 x squared evaluated from 0 to 5. Now plug in the bounds. Negative 1/2 of 0 squared minus negative 1/2 of negative 5 squared. It's a lot of negative signs. And then plus 1/2 times 5 squared and minus 1/2 times 0 squared. 0 plus, were these 5s or what were they? Yeah, they're 5. So we got plus 25 over 2. And then plus another 25 over 2, which is 50 over 2, 25. Oh, it's not an option. I forgot the 6. I gotta go back and put all the 6's in front. So there's a 6 there and a 6 there. Oops. Oh, got some 6's there. That's okay. So we have a 6 multiplied by this, and a 6 multiplied by that. I have a 6 multiplied by this, and then this multiplied by 6. So that's 150. That's better. That was a big time mistake. Anyway. Okay, next one, number 18. Determine integral of this function. So it's a type of problem that requires you to know a trick. And it's a trick that has been done in class. It's a trick that has been done on a quiz. So it's something you've seen several times already, and I think it's on one of those sheets as well. I think it's been everywhere. It's been on the handouts, it's been in class, it's been on the quiz, the practice test. Take a wild guess why. The trick for solving this is one of the most powerful tools in mathematics, the famous multiplication by 1. But you can't use any old one. You're going to multiply the function on the top and bottom by the same thing. You can multiply by e to the x on top and e to the x on the bottom. So we're going to use 1 equals e to the x over e to the x. Okay. Let's keep going. 2e to the x over 3 times e to the x, and then plus 4 e to the negative x times e to the positive x. Multiplying that in the bracket. Now we have an exponent law, e to the negative x times e to the positive x is e to the negative x plus x, which is e to the 0, which is 1. So we get integral, forgot the dx. dx, integral 2e to the x over 3e to the x plus 4 dx. Scarcely looks better, maybe it looks worse, but it gets us close. You can do the next step several different ways. The way that I like to do the next step is to let w equal everything in the bottom. Do a substitution. Let w equal 3e to the x plus 4. Then dw by dx is 3e to the x plus 0. Cross multiply. dw is 3e to the x, ignore the plus 0, times dx, then divide. dx is dw over 3e to the x. We can substitute our dx with that. Okay, now our 2e to the x survives upstairs for now. We didn't do anything with it. The downstairs got replaced with w, and the dx gets replaced by what was just found on the right. dw over 3 e to the x. We can celebrate because the substitution got rid of all the old variable. All the x stuff is gone. We have a few pieces to worry about. There's a 2 upstairs and a 3 downstairs. We can put both of those constants out front. So 2 over 3, antiderivative of 1 over w, dw. So all the pieces are accounted for. The 2, the 3, the w, the dw are all there. Now we take the antiderivative of 1 over w. We get ln absolute value of w, and there's no bounds of integration, so we have a plus c. Now we can replace w with what it really is. What our substitution says it was is 3e to the x plus 4. Plus c. And the next part's kind of technicality. It's reflected in multiple choice options though, so I'm going to mention it. E to the x, that's an exponential function, and it's never going to be negative. It's always above the x-axis. You can't get negative numbers out of e to the x. You only get positive y values out of that function. You multiply by 3, you're not going to make negatives, still positive. If you add 4 to it, it's even more positive. That's why we can drop the absolute value signs. You're plugging something that's strictly positive into the absolute value function. The absolute value signs are not necessary. So 2/3 ln of 3e to the x plus 4. So choice C. Okay, now part B. Part B is a derivative question, derivative of a trig. So trig functions are new for test 2, and sometimes there's derivatives, sometimes antiderivatives, sometimes both. This one wants a derivative. It's e to the power of a function. So my first step is to write down what type of prototype it is. It's an e to the w prototype, or an e to the u prototype if you use the letter u instead of w. when you take the derivative of e to the w, it's e to the w multiplied by w prime. That's the chain rule for an exponential function. And that's e to the 12 times the cotan of the root of x multiplied by something that could be a lot of work to do. I'm going to do that calculation off to the side. W equals 12 times the cotan of the square root of x. That itself is an involved derivative. It's a cotan of, I'll call square root of x u. Then w prime, the derivative of cotan, starts with letter c, so I'll have a minus sign, has a t in it, so it'll be something squared, and the thing that's squared is cosecant. So negative 12 cosecant squared of u, and multiplied by u prime. Okay, now u is the square root of x. Now we need u prime. So put that down here. U is x to the power 1/2. U prime is 1/2 x to the negative 1/2, which is 1/2 times 1 over root x, which is 1 over 2 root x. So this is 1 over 2 root x. Now we can simplify w prime. Negative 12 over 2 is negative 6. Cosecant square of the root of x all over root of x. And then that can get plugged in for w prime. So e to the 12 times the cotan of the square root of x multiplied by that big mess. Negative 6 cosecant squared of the square root of x over root of x. And then if we were trying to write the solution that would exist in the back of a math textbook, we would put the negative 6 in front. We would put the square root of x underneath the entire thing. I'm not sure where we would put the cosecant squared. We put it before or after the exponential function. Never really saw any type of consistent rule with that. But for this type of a test, it does not matter. Just leave it any old way. And number 2 in the long answer. This is going to be a giant pile of work because it's a third derivative. The third derivative of a function is given, and we have conditions on the second derivative, first derivative, and original function. We need all this information to find the original mystery function that matches all the conditions. To start things off, I'm going to take one antiderivative of the third derivative. That'll give me a second derivative. Derivative of x is 1/2 x squared. Derivative of 36 is 36x, and we get a plus c. Before doing anything else, I'm going to clean it up. 48 over 2 is 24, and then x squared plus 36x plus c. Now we're going to use the second derivative condition, f double prime. We're going to use that to find c. This says when x is 0, the function, the second derivative function is 3. I'm going to replace the function f double prime with 3, the x's with zeros, and plug in the rest. E equals 24 times 0 squared plus 36 times 0 plus c. So we're going to get c is equal to 3. 3 is equal to 0 plus 0 plus c. So my second derivative, f double prime of x, I'm going to rewrite it with that value of c, 24x squared plus 36x plus 3. Now we take the antiderivative again. F single prime of x is equal to, take the antiderivative of x squared, we get 1 over 3x to the 3. Let's multiply by the 24 in front. Take the derivative of 36x, we get 36 times 1/2 x squared. Take the derivative of 3, we get 3x, and we get a plus. You can call it c again if you want. I'm going to call it d. And then clean it up. We're going to have that f prime of x equals 24 over 3, that's 8, x to the 3, 36 over 2, that's 18, x to the 2, plus 3x plus d. So, we're going to use the condition on the first derivative to find d. That condition says when x is 1, the derivative is 32. So 32 goes there, 1, 1, 1. 32 equals 8 times 1 to the 3 plus 18 times 1 to the 2 plus 3 times 1 plus b. And then simplify. 32 is 8 plus 18, 26 plus 3, 29 plus d. And then subtract. d is equal to 3. So our function is f prime, or the derivative of our function, f prime of x, is 8x to the 3 plus 18x to the 2 plus 3x plus 3. Now we have to do it again. One more time. Take the antiderivative. Antiderivative of x to the 3 is 1 over 4x to the 4. Antiderivative of x squared is 1 over 3x to the 3. Antiderivative of 3x is 3 times 1 half x to the 2. And antiderivative of 3 is 3x. And now we have a plus, but we use c, we use d, maybe we should use capital E, but I'm not going to do it and use a. Ha! Take that. Now we clean it up. 8 over 4 is 2, 2x to the 4, plus 18 over 3 is 6, x to the 3, plus 3 over 2, x squared, sorry about the fraction, plus 3x plus a, and we have to find a. Thankfully we have one more condition. The question says f of 1 is equal, f of negative 1 rather, is equal to positive 1. So there we go, we're going to find a. So the condition says when the x value is negative 1, the function's value is positive. So 1 goes there, negative 1, negative 1, negative 1, negative 1, and fill in the rest. 1 equals 2 times 1 to the 4 plus 6 times 1 to, or negative 1 to the 3 plus 3 over 2 times negative 1 squared plus 3 times negative 1 plus a. And clean up. 2 minus 6 plus 3 over 2 minus 3 plus a. Okay, 1 equals 2 minus 6, so minus 4, and then minus 3 is negative 7 plus 3 over 2 plus a. Add the 7 to both sides, subtract 3 over 2 from both sides. So we'll have 8 minus 3 over 2 equals a. You can make common denominators. So 16 over 2 minus 3 over 2 is equal to a. That means a is 13 over 2. And if nothing was screwed up in here, you didn't make any mistakes, so it's a special type of miracle. And then the function f of x is 2x to the 4 plus 6x to the 3 plus 3 over 2 x to the 2 plus 3x plus 13 over 2. And if you had nothing better to do in the entire world, you could take the derivative of this 3 times and make sure, after doing that, you get the original function, 48x plus 36. And you could check each of the conditions on the function itself. You could plug -1 in, make sure you get 1 back. Then take the derivative. Plug 1 in, make sure you get 32. Then take the second derivative, plug 0 in, and make sure you get 3. Let's not and say we did. Okay, last question. Check the time again. Okay. It is a scary-ish looking antiderivative with unfriendly looking bounds. But there is clearly one function plugged into another function, and knowing that that's one of the hallmarks for what tells you what to use for substitution, we're going to try that and see what happens. We're going to try w equals a thing that's being plugged into another function, in this case 2 times ln of x. So we're going to start the substitution off. We have sine of w over x, and then the dx is going to have to be replaced. And we hope that when we replace the dx, it'll cancel the x that's downstairs. We're also going to have to change the bounds. So we can't forget to do any of that. We'll do one thing at a time. For the dx, these. And take the derivative of w. dw by dx is 2 times 1 over x, 2 over x. Now cross multiply. X dw is equal to 2 dx. Now divide both sides by 2. dx is equal to x dw over 2. So x dw over 2. Which is excellent news. It's wonderful news because there's an x on top that cancels with that x on the bottom, and the old variable is completely gone. We have an integral in terms of only the new variable. There's a 2 downstairs, so I'm going to put a 1 over 2 in front. Antiderivative of sine of w dw. But wait a second, we didn't do the bounds yet. That's next. So the bounds. We're converting from an x integral into a w integral. We have to convert our x bounds into w bounds. E to the pi over 2. Our function is w is 2 times ln of x. So we're going to have 2 times ln of e to the pi over 2. Ln e cancels, so you have 2 multiplied by pi over 2. The 2's cancel, you have a pi. So our top bound is a pi. Now we do the bottom bound. The bottom bound was 1. Our substitution is w is 2 times the ln of x. So that's going to be 2 times the ln of 1, which is 2 times 0. Ln of 1 is 0. Haunting you from test 1, perhaps. Let's go for that. So the bottom bound. Now we plug in. Now after plugging in the new bounds, we can take the antiderivative. We get a 1/2 in front. Antiderivative of sine of w is negative cosine of w. The derivative of cos is negative sine. I don't want the negative in front, so I need the negative in front of the function to cancel the negative that would come out if I take its derivative. Evaluated rather, from 0 to pi. Okay. Now I'll plug in the bounds. We'll have negative cos of pi and minus 1/2 times negative cos of 0. Cos of pi is one of the ones to memorize. Cos of pi is negative 1. And then cos of 0 is also something worth memorizing. Cos of 0 is positive 1. Now I can simplify negative times negative positive, so positive 1/2 there, another negative times negative positive, 1/2. and then 1/2 plus 1/2 is 1. And that's it.